All right, so we are talking chapter 8, I believe. So this is our solutions chapter here. So last time we talked about some different concentration units. We talked about sort of percent concentration units, like percent mass to mass, which is the mass of the solute divided by the mass of the solution times 100%. We also talked about percent mass to volume, which is the mass of the solute divided by the volume of solution times 100%. And lastly, percent volume to volume, which is the volume of solute divided by the volume of solution times 100%. In your book and stuff, they may use weight instead of mass, but same thing, basically. W to W is the same as mass to mass as well. So we talked about solving some of these problems. You can obviously use the equation. We also talked about that you could kind of, convert it into a conversion factor if you had something like 4.5% by mass, calcium chloride. That's basically saying you had 4.5 grams of calcium chloride and 100 grams of solution. Or again, you could flip that sort of conversion factor the other way. Grams of solution, 4.5 grams of calcium chloride. So we did a problem, I think, like that, where, you could go back into this equation, just solve for what's missing, or you can do more of a dimensional analysis approach and stuff like that. Out of all three of these, the most important one in terms of being careful is really this first one, and it is the bottom part here. And it's very common in those type of problems that they do give you the mass of the solute and the mass of the solvent sort of separate from one another. So it's very common people will just use the solvent mass rather than adding them together. So a reminder that when you get the mass of the solution, it is going to be the mass of the solute plus the mass of the solvent. The other ones, you don't have to worry too much about those because usually they just straight out just give you the volume of the solution. So it's just really that one with the grams you just have to be careful of. And like I said, it's very commonly those things are sort of split up. We also then got at the end there into really the most common unit of concentration, which is molarity. Molarity, which is capital M, is moles of solute over liters of solution. And we could rearrange this and solve for liters, which would be the moles divided by the molarity. We also could do a very common version here to solve for moles, which is liters times molarity. Remember that, I would highly recommend to sort of get rid of the big M as you're doing calculations, because it is very common people forget all about the liters part of it or the volume part of it, and they just kind of focus on the M and go moles. So I got moles, but I'm not really sure where the volume aspect of it. So what you could do with that is obviously just convert the big M into moles per liter. The number always stays with the moles and is always per 1 liter when you do it. So if we had something, thank you very much. If we had something like a 4.5 molar solution of calcium chloride, you could just take that big M and convert it into 4.5 moles of calcium chloride per liter. And you can really use it dimensional analysis way too, as like a conversion factor. If you need the liters on top, you could just do that and flip the moles on the bottom. And again, the benefit of this is hopefully you can see both units so you won't forget about the liters. The other common mistake that people make is they don't forget necessarily about the volume part, but they're not sure if they should multiply or divide. So you can sort of visually see what you need to do if you kind of get rid of the big M when you do calculations. Any questions on any of that stuff we talked about last time? Other things here is definitely with molarity, since it is moles per liter, very commonly we are given stuff in grams, so we got to go to moles using the molar mass from the periodic table. And the other for sure thing is it does need to be in liters when you're using it with molarity. So very commonly the volume's in milliliters, so you got to do that sort of conversion by 1,000 there to convert it into milliliters, and that's a really common thing, especially if you're just straight using volume times molarity, so that it properly cancels out and does give you moles, which is probably what you're aiming for. If you leave it in milliliters and you times it technically by molarity, what you technically have in this situation is actually millimoles over milliliters. Then the milliliters will cancel, but what you end up with is what is known as millimoles, not moles. So most of the time you'll be off by a factor of 1,000 probably in most of your calculations. If you do that, you'll be okay if you divide it back by milliliters and everything. So my recommendation is if you're using molarity standalone, make sure always just to convert it to liters, and you'll be in the right units probably for what you need. But you technically can take milliliters times molarity, but it actually gives you millimoles rather than moles. And that's because molarity really can also be millimoles over milliliters. And in this case, the millis will cancel out and you'll get back to moles per liter. So as long as you do both milli on top and bottom, you could get back to molarity. But just to keep it safe, convert it to liters and you won't have that sort of problem. Any questions on that there? Okay. So the next thing we're going to talk about is dilution. So we talked about sort of concentrations of solutions. Very commonly, most solutions will come to you in a what is sometimes referred to as a stock solution, which is a really concentrated type solution. Then typically what you do with that is you take it and you do some dilutions to it, and then you get kind of like the solutions you probably use in lab, which is way, way less in terms of concentration than other ones. So usually when we do a dilution, really the only thing that's added is the solvent. And in most cases, the solvent a lot of times is water, as it's a very common sort of solvent. A reminder, it doesn't always have to be water, but it is very commonly used. So what that means is when we do a dilution, the moles of the solute before the dilution will actually equal the moles of solute after the dilution. As you can kind of see here, if you count those circles, if they did it correctly, they should have the same number of circles as the circles are solute on each side there before and after. What ends up happening though is your molarity or your concentration goes down. And the reason for that, if we just look at what molarity is, it is moles of solute divided by liters of solution. So when we add more solvent, in this case, what we're really doing is increasing the bottom part there. And when we increase the denominator, the overall molarity actually comes down. So that is what happens. The top part doesn't really change at all. So there is a dilution equation, which is this one right here. M1 times V1 is equal to M2 times V2. Doesn't have to be this way, but most of the time, the first guys there are the more concentrated solutions. So the one with the higher molarity and volume that you're going to use of that solution. The second one there, or the twos, are typically the one that's more dilute. So if you solve for M1, that would be the concentration, the more concentrated one. If you solve for V1, that's how much of the concentrated one you're going to use. If you solve for M2, that's typically the concentration of your diluted solution, and V2 would be your volume of diluted solution in this case. Now, I know I just went over the whole thing where you should convert it to liters and all that when you're using molarity. This is the one equation where you don't necessarily have to do that as long as you use milliliters on both sides. So if you want, you can convert the volume to liters and you'll be fine. When you solve for volume, you'll just end up with liters. But if you want, in this particular equation, you can leave everybody in milliliters. Just for unit wise, if you took milliliters times molarity and we were solving for M2 and we divided by milliliters, the milliliters cancels out. So everything works out okay in this particular case. So as long as the volumes on both sides are milliliters, you could actually leave it in this particular equation. But if you are using molarity just by itself, not in this equation, you 100% do need to make sure you convert it to liters. Otherwise, again, you probably will be off. Any questions on that there? Now, sometimes people will show the dilution equation as C1 V1 is equal to C2 V2, where C is just a generic concentration. And the truth is, although molarity is really the most common unit of concentration, and most people roll out the dilution equation as M1 V1 equals M2 V2, you could use any type of concentration unit in here. So you could use your percent mass to mass on both sides. You can use your percent volume to volume on both sides and so forth. So sometimes people will roll with kind of a more generic version of this equation, where C is just any type of concentration unit that you want. But probably 9 times out of 10, you're going to have molarity, and you're going to want to go with the guy on the left there. Any questions on that there? So when we do a dilution, you know, we usually have a more concentrated solution. And basically what we do is we take some of it out, we put it into a new container, and then, like I said, we typically add some more water or solvent to it. We get it a nice mix, and then obviously our molarity will come down. So let's take a look at one here, I think. What is the concentration of a solution formed by diluting 5 milliliters of 3.2 molar glucose solution to 40 milliliters? I don't think that's supposed to be a comma, so that should be probably 40 there. 40.0 milliliters. All right, take a couple of minutes here, see what you come up with. Okay, let's take a look. So we're taking a glucose solution. We want to know what the concentration will be if we diluted 5 milliliters of 3.2 glucose to a final volume of 40 milliliters. So really our M1 here is 3.2 molar. Our V1 is 5 milliliters. Our final volume here is 40 milliliters. And we are looking for what our new sort of concentration will be here. So we could use our M1 V1 is equal to M2 V2. In this case, we're going to solve for M2. So we're going to divide the V2 to the other side. And when we do that, that gives us M1 V1 divided by V2 is equal to M2. Now, in this case here, I'm going to put in my numbers. So my M1 is 3.2 molar. My V1 is 5 milliliters. And my V2 is 40 milliliters. So in this case, because I got milliliters on both sides, technically when I times the top guy by molarity times milliliters, I get millimoles. And then when I divide it by the milliliters, I go back to molarity. So you don't have to convert it to liters here, but if you wanted to, you could. It should come out exactly the same. Here, though, the milliliters will cancel each other out. And that would get me 3.2 times a 5 divided by a 40. Gives me a concentration of 0.4 molar here. Question on that calculation. Now, if we were to make the solution just the way it said, right, we would have a bottle that is sitting there that has a molarity of 3.2 molar. We would take another bottle here that we're going to make our solution in. We would take out from here and put in 5 milliliters of our glucose solution. The rest would be water in this case, yes. How much water would I put in there? Would I put 40 milliliters of water? I would not put 40 milliliters of water, because if I did, my total volume would then be 45 milliliters, right? Which means my molarity would not be correct. So a very common sort of dilution question is basically how much water would you add? And to find that, it really is a lot of times just taking V2 minus V1. I'm going to end up with 40 milliliters in this case. I already put in there 5 milliliters. That means we need about 35 milliliters there. Not 350, 35 milliliters of water in this case. So I would fill the rest up here with 35 milliliters of water. That gives me a grand total of 40 milliliters, which is what I want to make. Give it a nice mix. And if I do all that, I should now have 40 milliliters of a solution that has a molarity of 0.4 molar. Any questions on that there? All right, so why don't you try one here? Let's say we had let's do how much water would need to be added to (15 milliliters of a, we'll go 18 molar sodium hydroxide solution to make a solution that has a molarity of 0.9 molar. All right, take a minute or two to see what you come up with. All right, let's take a look. So once again, we have the more concentrated solution there. So our M1 would be 18. Our V1, we're just going to use 15 milliliters of it. And we're going to shoot to try to make a solution that has a molarity of 0.9 molar. So clearly, if you're not sure, we don't have V2, so that would be a good place to start. So using our M1, V1 is equal to M2, V2. Solving for V2, we're going to divide the M2 to the other side. Going to give us M1, V1 divided by M2. Putting in our numbers here gives us 18 molar times 15 milliliters divided by 0.9 molar. And once again here, I don't need to really convert it to liters, but you can if you want. The deal here is the molarities are going to cancel, which just means when I solve for it, I will be in milliliter. So if that's not the unit you want in this case, you might have to do a conversion. So 18 times 15 divided by a 0.9 there gives us something like 300 milliliters. Is that the answer here? That is not the answer. That's actually 300 milliliters of my total volume that I'm going to make, right? And that's usually what you get when you solve for V2. So the volume of water would be found by really taking my final volume minus my initial volume. And if we did that, that would be 300 minus 15 milliliters. Going to get us something like 285 milliliters of water. So once again, if we were to make this, we would go over to our 18 molar guy. We would take out and put it into our new container, our 15 milliliters of it. We would then add in 285 milliliters of water, giving us our total volume of 300, which is what we need. And again, when we mix it together, we then should have a solution that has a concentration of 0.9 molar. Any questions on dilutions here? Okay. Yeah. Yeah. So I would say in a dilution problem like this, if it asks for water, how much water you need to add, which is a very common question, you usually have to do that extra step of subtracting the two volumes. Now, if it just asks, for example, maybe like the first question was, what would the molarity be? Then you're going to solve for M, and that would be your answer. Or if it asks what the final volume would be, that would be it. Or if it asks what your initial volume or how much of the more concentrated one you would use, that would be sort of one step. So it's really only in a dilution problem where they ask something about how much water you should add. You got to kind of take that extra step to know that you got to subtract the difference. Other questions? Okay. So we're going to finish up here in this chapter talking a little bit about colligative properties. Colligative properties of solutions basically depend on the concentration of the solute, really not its identity. So colligative properties are really based on how much junk is floating around in the solution. The more stuff floating around in a solution, the more solute floating around in a solution, it has a greater effect on the property of that particular solution. It can make the boiling point, for example, increase. It can make the freezing point decrease, which is sometimes referred to as freezing point depression. So what we're talking about is if we took just, for example, say pure water by itself. We'll use our red circles to represent water, I guess. There we go. So if we decide to heat just water, which is a pure substance here by itself, you know, we get it to like 100 degrees Celsius and we're going to get some boiling going to happen. And that's going to allow these water molecules to gain enough energy really to sort of escape to the surface there and go off and basically make steam, right? Like we boil some water for pasta, starts steaming right as it starts boiling and stuff like that. Now, if we take the same sort of water, for example, and we'll put our little water molecules there, but we decide, hey, let us, you know, add some stuff in there, maybe like some sodium chloride or some salt along the way. So now we got all these other particles kind of floating around in there. And what ends up happening is as you go to heat it, it takes a little bit more energy for everybody to get out of there because frankly, there is a lot of stuff in the way. So now these water molecules no longer really have like a free path to kind of get out of there. They kind of have to weave themselves around, and it's going to take a little bit more energy to do that. The result of that is we're going to see actually the boiling point increase. So instead of maybe boiling at 100, it will boil at 102 or 105, depending on what you put in there. The same thing happens with like freezing. So if this water was going to freeze, we'll get rid of our heat. If this guy is going to freeze, these water molecules would basically lose energy and sort of come together and come into like ice. Now, if again, we get rid of this and we decide to throw it in the freezer in this case, same thing's going to happen here. But once again, there's a lot more stuff in the way for these water molecules to kind of get to each other to really freeze. And it's going to cause it to actually freeze at a lower temperature. Like you put some rock salt and some ice, right? You can make some ice cream. It gets really cold. Yes, it gets a lot colder. So the presence of particles like in a solution versus the pure solvent will definitely affect things like boiling point or freezing point. Also affect things like vapor pressure as well. By the way, that's why we put antifreeze in our car, right? It raises the boiling point and it also will lower the freezing point in case you live in a really cold area. All your water and stuff inside your car will not freeze. It has to get really, really cold for that to happen. And obviously, if you live in a really hot area, it takes a lot higher of a temperature for things to really start to boil and overboil and stuff like that. And that's really the purpose of something like antifreeze. That's why you mix it with some water and you put it in there. So when we talk about boiling point elevation, if we have something that's a volatile solute, volatile basically means that it can go into the gas phase easily. So it can readily just kind of go into the gas phase. There's lots of things, especially those guys that have those dispersion forces that we talked about, which a lot of organic guys do. They could go into the gas phase really, really easily. A non-volatile solute does not readily escape, so it has a negligible vapor pressure at a given temperature. The vapor pressure above the solution of a non-volatile solute is lower than the vapor pressure of the pure solvent. So that's what we call vapor pressure lowering. So above the solution, in any solution, there's always guys that are escaping into the gas phase above it. So right at the surface of the liquid, you basically got guys going into the gas phase and you got guys dropping back down into the liquid phase. So obviously these guys escaping into the gas phase will create gas, right? Basically above the liquid. and gas creates pressure, and that is what is known as the vapor pressure. Is basically the pressure exerted by the gas molecules that are right above the liquid surface. You get even more vapor pressure if you kind of lock it in there. You can't really escape those gas molecules, so it keeps that pressure above the liquid surface. So what happens in terms of having more guys in there dissolved in this sort of solution is, once again, it gets in the way of those guys being able to escape to the surface. So less of the solvent molecules can escape to the surface, which means you have less gas molecules above the liquid. Less gas molecules means what you'll see is the vapor pressure will come down because of that. Because they're getting in the way of the process that occurs. So the effect of this is we see what is sometimes referred to as vapor pressure lowering. And again, what happens when we do dissolve some solute into the solution is we end up getting less gas molecules above the liquid. And the result of that is our pressure will come down because we have less gas molecules, again, kind of floating above the liquid. Any questions on that there? As I mentioned before, in terms of the boiling point, it does tend to elevate it. Again, it just gets in the way of the solvent naturally sort of being able to escape and go through boiling. Obviously, those guys floating around will also absorb some of that energy, right, as you're heating. So again, it takes a little bit more energy to get everybody to start to boil. And again, depending on, what it is and how many particles could have a greater effect. So if you dump something, for example, like sodium chloride into a solution, you get a sodium ion and a chloride ion that's basically flying around or floating around. If you dump something like calcium chloride into a solution, you get a calcium ion and you actually get a couple of chloride ions floating around. That's going to have a bigger effect on it because there's now more particles basically floating around. So when you drop an ionic guy into a solution, depending on how many ions it breaks apart into, can have a greater effect on things like boiling point and freezing point depression. It is sometimes referred to as the I factor or the von Hoff factor. And we use that for ionic compounds because, again, they don't create basically a one-to-one relationship when they go for a swim. If you have something that is non-ionic, so sort of molecular or covalent, like glucose, for example, when you put that in there, you basically get a one-to-one ratio. So for one glucose molecule you dump in there, you get one glucose molecule that's floating around. But again, ionics is different because you do get different amounts of ions, which will affect the overall change that you see. Freezing point depression, as I mentioned a second ago, again, will be lowered by having these products there. Again, it just gets in the way and causes a much lower energy for everybody to freeze. You got to take out more energy to do that, as we've got those guys basically floating around. Talk a little bit about osmosis and dialysis. Osmosis is a natural process where solvent molecules move from a lower concentration to a higher concentration in an effort to sort of dilute down the more concentrated solution. And what we typically have a lot of times is a semi-permeable membrane. So if you have a membrane right about there in this tube, and a membrane basically allows particles to pass through, and it's sort of size restricted, although with your naked eye you can't really see it, but there's basically holes in it. And there's basically holes, which means if you get a giant particle trying to get through there, it's not going to be able to get through it. So it's obviously going to be blocked out. It will allow, smaller things like solvent molecules, to sort of pass through those holes with no problems. But, the membrane basically has sort of a size filter on it, like our cell membranes, right? It has sort of a filter on it, unless certain size things kind of pass through. Other things are sort of restricted as it goes through there. So if we have on one side of the membrane, say some salt water, and on the left-hand side, we had just pure water in this particular case, the process of osmosis will occur in basically the water molecules over here on the left, which is less concentrated, will start to flow across the membrane into the saltwater side, again, in an attempt to basically sort of dilute it down. It will continue to flow until it hits a certain point, which is known as the osmotic pressure. The osmotic pressure is basically kind of equal to atmospheric pressure. It at some point will stop the flow of water molecules across that membrane because it kind of pushes back down on it, and it will sort of dilute it. That is what happens, sort of the idea of what you maybe have heard of reverse osmosis. Yes, reverse osmosis, you got kind of a similar setup. And so you got your salt water or whatever on this side and your pure water on this side. You hit that osmotic pressure, then you apply a pressure greater than the osmotic pressure. What that's going to do basically is push everybody back the other way. And if you have a good membrane or filter there, you're going to catch all the crap. You don't want to go to the other side, right? And you'll end up with something like pure water when it's all said and done and stuff like that. So that is what is referred to sort of as reverse osmosis, which is basically forcing everything out the other way. Any questions on that there? Here's a prettier picture of what we were talking about. Again, this is our membrane allowing certain size molecules to freely pass through. Obviously, these bigger guys right about here, he's going to have a little bit of trouble kind of getting through that. This leads us to the idea of osmotic pressure and its effects on things like cells, for example, the classic red blood cell there. There's like really three types of solutions. There are what are known as isotonic solution, which is what we see here. There are what is known as hypotonic solution. Hypo means less than. And there are solutions known as hypertonic, which is basically more than. Now, what constitutes an isotonic solution? An isotonic solution is these two solutions right here, basically 0.9% sodium chloride, or sometimes referred to as a saline solution, could really be any type of ionic compound like that, and 5% glucose. What is an isotonic solution? Well, they're typically solutions they use, for example, in things like IVs, because if you're probably having an IV, you don't want the wrong pressure balance there for your cells. What it basically means is, as you can see in that nice pretty picture over there, if you take something like a red blood cell and you put it into an isotonic solution, what you're going to have is basically equal pressure outside and inside of the cell. So you're basically going to have a nice even kind of flow of guys working in and out of the cell, where the cell is sort of acting as the membrane, right? Just allowing things to flow in and flow out of it. So those two numbers are really important because it helps you determine whether or not you're dealing with a hypotonic solution or a hypertonic solution. So you should put a little star next to those because those are sort of your reference point for these type of questions. So let's take a look at what would happen if we put that same red blood cell into a hypotonic solution. So a hypotonic solution, as I mentioned before, is basically less than. And what's going to happen is on the outside of the cell is less concentrated than inside the cell. And based on osmosis, that means that outside of the cell is going to go, that guy is way too concentrated. So osmosis is going to bring all the fluid from outside of the cell into the cell, which means if you are that cell, you're going to start to feel a little bloated. Yes, you're going to start to swell and get bigger and bigger. It will eventually burst, usually, which is probably not a good thing if it's your cells. And that is what is known as hemolysis. So basically, through the process of osmosis, Basically, the cell kind of absorbs all that outside solution, causing it to swell and obviously burst. Any questions on that there? Now, what happens though if we put it into a hypertonic solution? Hyper means more than, so outside of the cell is actually more concentrated than inside of the cell. So the opposite is going to happen. The cell itself is going to go, whoa, outside of me needs some dilution. So it's going to basically flow out all of its liquid. And when it does that, it's going to cause the cell to shrink. And that is what is known as crenation. Also, probably not so good as well in this situation. So it's only really isotonic solutions which have basically the same osmotic pressure inside and outside of the cell that they exchange fluids sort of equally. It's when you have a hypo or hypertonic solution that you do run into some issues. Any questions on that there? Water has no osmotic pressure, because if you have pure water, you got nothing floating around in it. So osmotic pressure is basically related to how many particles that you have floating around. Sometimes people calculate a sort of version of osmotic pressure, which is known as osmolarity. And osmolarity is that I factor times the molarity. So to give you an example of that, let's say we took two ionic solutions. One was 2.5 molar sodium chloride, and one was 2.5 molar calcium chloride. So once again, as we talked about earlier, when sodium chloride breaks apart, we get one sodium ion and one chloride ion, which means I, in this case, would equal 2. There are 2 particles that basically are floating around. So if we wanted to calculate the osmolarity, which is sometimes referred to as osmol, of this solution, we would take the 2, which is our factor there, and times it by 2.5 molar, and we would end up with 5 osmolarity, right? So if we look at the next solution, which has the exact same molarity, but it is a calcium chloride solution, it breaks apart into a calcium ion and 2 chloride ions, as we talked about earlier. That means I, in this case, will equal 3. So when we now go to calculate our osmolarity here for this guy, we would take 3 times our 2.5, and that's going to give us 7.5 osmolarity here. Which one should exert the higher osmotic pressure? It is going to be the calcium chloride over there, as it has a higher osmolarity because it has more particles basically floating around in that solution. Even though they both are the same molarity, because there is greater number of particles in that calcium chloride, it actually will exert more pressure in that case. And then again, that's why it would probably affect some of that solution a little bit more. Any questions on that there? Okay, so let's see here. Let's actually do a couple of these here first. Let's go. Yeah. Let's go here. So for each of the following here, I'm going to write, try and get rid of this here. Decide, will this red blood cell shrink? Will it swell? Will nothing happen to it? So if we put a red blood cell in a 0.5% sodium chloride solution, we put it into a 10% glucose solution, we put it into water, and we put it into a 0.9% sodium chloride solution. Will the red blood cell shrink? Will it swell? We'll go through crenation or homolysis. Okay, let's take a look. So we're at first one here, 0.5% sodium chloride. These are isotonic solutions. So for sodium chloride, it needs to be really 0.9%. So it is as simple as 0.5 is less than 0.9, right? So that means we are dealing here with a hypotonic solution. It is less than. Because it's hypotonic, what's going to happen is the outside of the cell is actually less concentrated than inside of the cell. And that means all the water is going to rush into the cell in that particular case. And it is going to cause it to swell, right? And burst, which is hemolysis. Yeah. Any questions on that one there? Going to number 2, which is 10% glucose, comparing that to our 5%, which is isotonic. So our 10% is definitely higher than 5%. That means that this is a hypertonic solution. That means the opposite is going to happen than what I just drew here. In this case, we got on the outside of the cell more concentrated than inside of the cell. So basically all the water in the cell is going to come out of the cell in an effort to dilute down the solution. The result of that is we should see some shrinkage, and that would be crenation here. Any questions on that one? How about pure water? It is hypotonic, yeah. So pure water is actually hypotonic. Again, it has nothing in there. It has no osmotic pressure, which means it's going to obviously be less pressure than the cell. And the same thing is going to happen here. Basically, the hypotonic as the first one, all of the water is going to rush into the cell, cause it to swell, and go through hemolysis. Any questions on that one? And then lastly here, 0.9% is our isotonic solution, which means we're all good. Nothing bad's going to happen. That's the happy situation, I suppose. Like, yes, sir. Yeah, I know it specifically says 0.92. Most books go with about 0.9. So we'll go with 0.9 because that's what I have in my head for most books. But yeah, in that 0.9 range is typically where you kind of cut it off for the sodium chloride. Yeah. Other questions? All right. So just to finish up here on this thing, last thing we're talking about is dialysis. Dialysis is a similar sort of process. A lot of times if you use dialysis, for example, in a laboratory, you sometimes will take a dialysis bag. Also has holes in it that you can't really necessarily see. But you can put like whatever your solution in or your protein or whatever it may be, and you could drop it into like an environment solution that's maybe at a specific pH. So say you were doing an experiment where you wanted to take a protein that you're maybe working on and you want to do it maybe as like the same pH you would find in the body. So you could put it in a dialysis bag, you could drop it into the beaker that has a solution that has that pH, and it'll sit there for a while and basically equilibrate to that pH, and then you could go do your research. Obviously in our bodies, right, we do dialysis basically, right, to get waste products out. So it allows waste products like urea to be removed from the bloodstream and eliminated in the urine. And obviously if your kidneys don't function good enough, you will sometimes need basically dialysis done for you by a machine to sort of filter out sort of the impurities that's in your body. But same idea. Basically everything kind of goes through the machine. It has some filters obviously, and it filters out all the stuff that you don't want to keep and comes back in and obviously back into your body. Any question on any of that stuff there? Okay, that wraps up chapter 8. Okay, the next chapter we're going to talk about is acid and bases. I hope it's chapter 9. All right, so let us get into acid and bases. So acids were first recognized by their sour taste. some examples of acids like vinegar is, or acetic acid is a major component of vinegar, citric acid there in lemons and so forth. Acids do react with metals in a single replacement reaction that we saw when we talked about reactions. So if you took something like zinc and you reacted with hydrochloric acid, and again, the zinc would come in and kick out the hydrogen, making some zinc chloride and some hydrogen gas in this case. And you would see some bubbles form there. Suppose I should do a little balancing like chemistry here. There we go. So you would form some gas bubbles here. So a very common sort of reaction that occurs. Also, acids react with carbonates, like say sodium carbonate in a double displacement reaction where these two guys basically switch partners and basically will form a little sodium chloride and some H2CO3, which is actually carbonic acid. Carbonic acid doesn't hang around a very long time. It very quickly goes through a decomposition reaction. We'll go down this one. And it oftentimes will create CO2 and water. But kind of like an Alka-Seltzer, plot, plot, fizz, fizz, right? All the fizzing and stuff, right? Are those antacid commercials. So that's the CO2 that you see sort of fizzing when you do that. Bases, on the other hand, are characterized by a bitter taste. Don't taste any acid and bases, please, in lab. And a slippery fill. A lot of soaps are bases. A lot of drain cleaners are bases. You can go to Home Depot and just buy straight sodium hydroxide to clean your drain. Comes in a bag with gloves and tells you a lot of warnings, but you can do that basically. A lot of bases come from group 1 and group 2 on the periodic table. A lot of strong bases come from group 1 and 2 on the periodic table. So things like sodium hydroxide, potassium hydroxide. And if you remember our names of these two groups, right? Group 1 is the alkali metals. Group 2 is the alkaline earth metals. The word alkaline means basic. So if somebody says, hey, this is alkaline, it means that it is basic. And again, like I said, a lot of really strong bases do come from that group 1 and 2 on the periodic table, kind of where lithium is down to potassium, hanging right at potassium, and then kind of up, down through calcium, strontium with hydroxide are very strong bases. So a very early definition of acid and bases was done by a guy named Arrhenius. He did a lot of work with electrolytes. If you remember, electrolytes are guys that basically will break apart into ions in solution and conduct electricity. He defined an acid as being able to produce hydrogen ions in solution. So what we are talking about there is on the product side, you get H+, which is the hydrogen ion. While he defined a base as something that's able to pretty much on the product side produce hydroxide. And when we're talking about this, we're talking about being able to, in a solution, produce H+ that is not attached to anybody, just is floating around freely in the solution. Or if we're talking more of a base, able to produce hydroxide, which once again is not attached to anybody, just basically floated around free in the solution. One thing that's important in acid-base chemistry is the H+, which is the hydrogen ion, and H3O+, which is the hydronium ion. Is essentially the exact same thing. So I personally use H+ most of the time, but pretty much anywhere I lay up an H+, you could lay up an H3O+. That goes in equations. It also goes in formulas as well. So books typically will use H3O+ in the formulas and stuff like that. Like I said, I just have H+ in my head. So I use H+ a lot. So you can really swap it out pretty much any way you do it. The real reason why you do get kind of the difference is it's really sort of how you write the equation. So for example, if we took something like hydrochloric acid, which is a strong acid, there's basically two ways that you could write that equation to represent it basically breaking apart in solution. So if we put that HCl into this solution, it would 100% break apart into its chloride ions and its H plus ions. So one way you could represent that is simply just taking the HCl and doing an arrow and writing H plus and H3O plus. Now, you could also write this showing the water's involvement in this reaction. And even though it's really not doing much other than kind of letting it break apart, it's still there. And you could write HCl plus water. And what's going to happen is the HCl is basically going to toss off an H plus over there to water. And when you do that, what you will make is H3O plus and Cl minus. And I wrote the wrong thing above there. I jumped that gun on H3O plus. So let's try that again. Sorry about that. That should be chloride, obviously, here. So that guy should be Cl minus. There we go. So what we see here is if you include water in your reaction or your equation, you will produce H3O plus. If you kind of leave the water out, you will produce H plus. They both really represent the acid part of the solution. And for all intents and purposes, they are basically equivalent to each other. And like I said, you'll see people kind of use them both, H plus and H3O plus. Any questions on that there? Okay, so let us then take a look here. If we wanted to make an acid like hydrochloric acid, we take some hydrogen chloride gas and kind of bubble it through water, and we will get basically H plus and Cl minus form. This is why acids typically will have that aqueous symbol next to them. I think we talked about when we talked about naming. All acids will always have this aqueous symbol because they're basically a water source of it, or in the water environment. If you had HCl, which is a gas, that is hydrogen chloride. Throw it through some water, you now get the acid, which is hydrochloric acid. So typically speaking, all acids will have that aqueous symbol next to it. And if you remember, I believe we talked about naming acids in here, right? It's all about whether or not it has oxygen or not. If it does not have oxygen, it starts with hydro and ends with ic, which is why HCl is hydrochloric acid. If it does have oxygen, a reminder that it has one of those polyatomic ions like nitrate. This becomes nitric acid, right? Or if it has one that is nitrite, ITE, this becomes nitrous acid. So a reminder that if the acid does obviously have oxygen in it, you do not use hydro. Hydro is just for acids that do not have oxygen in it. And if it does have oxygen, again, the one that ends in 8, the polyatomic ion should end in ic, and the one that ends in ite should end in OUS acid. Same thing happens. You take some solid sodium hydroxide, dissolve it in water, you will get the ions that are floating around. So it's not until it kind of goes into the water that it really does become an acid, because we have just generated a bunch of free floating around H pluses. Same thing with our sodium hydroxide here. When that goes for a swim, we generate a lot of hydroxide guys in that solution, which makes it a base. It was a good step sort of forward in acid-base chemistry. But he did a lot of work with a limited number of bases that really had hydroxide in it. So a lot of guys from group 1 and group 2 that actually has hydroxide in the formula. If you have a base that has OH in it and it is somebody from group 1 and group 2, there's a very good chance that it is a strong base, which means it's a strong electrolyte, which means it will 100% break apart in solution. But not all bases actually do have hydroxide in the actual formula. So an example that we will see in a second as well, I think, is a weak base like NH3, which is ammonia. And ammonia, when it reacts with water, will actually pick up an H plus from the water. And when it does so, it will create NH4 plus, which is ammonium, and our hydroxide. So something like ammonia is still a base. It is a much weaker base than something like sodium hydroxide, because the sodium hydroxide pretty much has the hydroxide with it. So it just needs to go for a swim and it produces hydroxide really quickly. Something like ammonia has got to go find some water, do a little reaction, and produce a little bit of hydroxide. So it's a much weaker base because of that, but it is still considered a base because ultimately it is still able to produce hydroxide in solution. So this is a very good example that not all bases have OH in it, but what we're looking at is whether or not it can produce OH minus in the solution, and if it can, it will be a base. Any questions on that there? So this sort of exchange of an H plus here, as we saw here in a second ago when I did the HCl, this is really actually the more sort of general definition of an acid and base that we look at, and a more generic or general definition of an acid and base, which you could apply to a lot more things, is what is known as the Bronsted Lowry definition. And in the Bronsted Lowry definition, an acid is a proton donor. That also is what an H plus is sometimes referred to as a proton. And that is because hydrogen has one proton, right? One electron, no neutrons. So in order to become positively charged, it had to lose its electron, which leaves it just a proton, which is what is left over at that point. So a Bronsted Lowry acid is somebody that will give up an H plus, and a Bronsted Lowry base is somebody that will accept an H plus. It is really important and very much overlooked a lot of the times, the plus part of it. The plus part will affect the overall charge as somebody loses an H plus and somebody gains an H plus. If you lose an H plus, do you become more positive or more negative? You become more negative, right? You lose an H plus, lose a proton, got more electrons, become more negative. And if you accept the H plus, you become more positive in that case. So sometimes people focus a lot on just the H and forget that the charge actually changes as well when you sort of lose and gain electrons. So it's really important to keep that in mind. Now, there is sort of a consequence that sort of occurs as we have a Bronsted Lowry definition. So if we look at HA, which is just a generic formula for an acid, in this case, what's going to happen is the acid here is going to donate its H plus over to the water. The water in this case is going to act as the base and going to accept the H plus. The result of that is on the product side, we form two things that are related to the reactants. So let's take a look at the acid. When we look at the acid over here, it is going to be related to this guy on this side because it has lost an H plus, and that is what is known as the conjugate base. So the acid on one side is related to the conjugate base on the other. So these two guys are related to each other. And the same thing happens with our water, which is acting as a base. Our water here is going to act as a base. When it accepts that H plus, as you mentioned a second ago, it becomes positive and forms H3O plus. And that is what is known as the conjugate acid. So the base on one side is related to the conjugate acid on the other side. These are what are referred to as conjugate acid base pairs, basically. The absolute only difference between the acid and its conjugate base, or the base and its conjugate acid, is this guy right here. It is just one H plus difference. So in order for something to be pairs, the absolute only difference that there can be is just that one H plus. And it cannot be more than one H plus. It has to be just one H plus for them to be related to each other. And in the case of the acid to the conjugate base, it has one less H plus. And obviously going the other way from the base to the conjugate acid, it picks up that H plus. So it has one more H plus as you go that way. Any questions on that there? Okay. So here's with our hydrochloric acid as we write it with the water there. But our conjugate acid base pairs are, again, two things that basically are related to each other by the difference of just that one H plus. So once again, here our HCl is going to donate, making this our acid, making once again here our water, our base. The HCl will create this guy over here, which is the conjugate base. And obviously, just like we saw over there, this would be our conjugate acid. Regular acid and bases, Bronsted acid, Bronsted bases, or regular acid and bases, always found on the left-hand side of the arrow, always the reactants. Any conjugate guy, conjugate acid, conjugate base, always found on the right-hand side of the arrow on the product side. So that is always where you can find those guys basically located. Any questions on that there? So here's just a drawn out reaction of what's happening there. And again, in this case, since water is included, we see we do produce the hydronium ion. And again, this is equivalent to just doing the H plus and the Cl minus. So let's take a look at one here. Which of the following represents conjugate acid base pairs? So take a minute or two and see which of these sets would qualify as a acid base pair. Okay, let's take a look since we're getting to the end here. So really what you're looking for is pretty much this, is the difference 1H plus. So that's what we're looking for. So if we look at the first guy, we got HClO4 and ClO4 minus. You could do it one of two ways. You could take the H off of this guy, right? And then also the plus should then make me one more negative, and they do match. So that would definitely be a pair. Or you can put the H plus back onto this guy, and it should match the guy on the left there if you like to do it that way. How about HCl and ClO minus? The difference here is 1H plus, but it is also a difference of oxygen there, no oxygen there. So those two guys are not related to each other. That's hypochlorite and hydrochloric acid. If we take our H2PO4 minus and our HPO4 2 minus, once again, if we take away an H, we're left with one H, and then we should then become one more negative, which then matches. So that means that those two are related to each other. And lastly here, HNO3 and NO3 minus, once again, scribbling out that, and then also becoming one more negative. I see they match, so they are pairs as well. So it looks like it is 1, 3, and 4 are all pairs in this case. Any questions on that there? Okay, we will stop here for today.